All right, our focus today is geometric probabilities. Okay, and you've worked with probabilities before, but maybe not in terms of what would we be looking at in geometry. So what is geometric probability? Well, if you remember what probability was, probability compares whatever you're looking for, how many ways that you can get what you're looking for, like rolling a dice, getting an even number. You would figure out how many outcomes there could be that would classify as an even number, and then take that compared to the total number of outcomes. They call it in the sample space. That would mean like all the possible things that could have come up. Like on a dice, you could get 1, 2, 3, 4, 5, 6. So when we were doing probability in your algebra class, you were looking at how many outcomes there are and how many you get that fit the category that you're looking for. You could list things, basically. Now, if you're looking at geometric probability, you're not able to make a complete list. Like if we're looking for all the points on a number line that fit a certain category, there are an infinite number of points on a number line. So you really can't list out what's called the sample space. And so we're going to be doing the probability based on calculations, like lengths or areas, not on the ability to list all the possibilities and see which ones fit the category. So it's a little bit different type of probability. So geometric probability is used when an experiment has an infinite number of outcomes. Like if you cannot list all the possible ways that this could happen. Did anyone else have quizzes or tests I need to collect? Yes, this is yours. Anybody else? Okay, so geometric probability is the probability of an event is based on the ratio of geometric measures such as length or area. In other words, as I said, you cannot list all the possible outcomes, so we interpret it in the area or length mode. So the outcomes of an experiment may be points on a segment or in a plane figure, like the area of it, because it would be covered by lots of points. There are three main types of models we're going to look at. One that would be a length model, an angle measure model, and then an area model. And those are the three that are in your chart for your notes. Finish the notes. The length model is basically a number line or part of a segment. Okay? The sample space, we would be looking at the whole segment that is in our picture, or we're going to like use a story and interpret it into a number line idea. If the event that we're looking for is all the points on segment BC, what we're going to do in this type of a model is figure out the length of BC and compare it to the length of the whole segment AD. So we're kind of saying what part of that whole segment is BC. So that'll just be comparing lengths. The second type, you might think of a spinner. Now the second type could be interpreted two ways. You could do area, but one way to go is just the angle measure. So the angle measure idea in probability, if we want to find the possibility or probability of something being in the blue shaded region out of the circle, instead of just doing area, we could find the degrees of this central angle, the degrees of the angle for that blue section, compared to the degrees of a whole circle, which would be 360 degrees. That's probably just a little bit easier than doing this one in the area model. So it would be comparing the central angle to 360. The area model, which you could do that spinner in an area model, basically the area model, you're comparing the area of what you're looking for to the area of the whole thing. So if we're interested in what's the probability of hitting a point or selecting a point in the triangle, we would take the area of the triangle, 1/2 base times height, for the numerator, and your denominator would be the whole rectangle's base times height. It's not blue part to white part, that is odds when you compare hitting it and not hitting it, that kind of idea. What we do in probability is compare the area of what we're interested in to the area of the whole thing. So there's a little bit of difference between odds and probabilities. Looks like you got your pictures drawn. Let's try some samples of each one. Here's a simple type example of number line. So I've got a simple number line, PQRS. A point is chosen randomly on PS. And how many points are on segment PS? Hope you're not saying 2 or 4. 25? Infinite. There's an infinite number of points. So that's why it's a geometric model. You really couldn't count exactly how many separate points are on there, but you can compare the lengths. So if we're looking for a point that's on RS, how long is segment RS? 5. Compared to the whole length of it, which Jack said was 25. So the probability here is simply 5 out of 25, which reduces 1/5. Just the length of RS compared to the length of the whole PS segment reduced. Probabilities can be expressed in fractions. They could be in decimal. They could even be in percent. I would say fractions are probably used in our book, or I'll use fractions if you can reduce it nicely. If not, then we'll probably go to a decimal and possibly even record it as a percent. So how would you get 1/5 as a decimal? 1 divided by 5. And then once you get that 0.2, how do you get that into a percent? Percents are out of 100. So you move the decimal like 2 places, so it's 20%. So all of those answers really are the same, 1/5, 0.2, or 20%. Okay, let's try an OR. What's the probability that a point is on segment PQ or segment RS? An OR means it could be either place, and it counts. So do the length of PQ plus the length of RS for your numerator. So PQ is 7, RS is 5. You can either do the probabilities separately, like 7 out of 25 plus 5 out of 25. You can add it separately, or you could add it together to begin with. I'm coming up with 12 25ths. 7 and 5 makes 12, 12 out of 25. What's the probability of the point being on QR or RS? QR or RS. That would be just adding 13 and 5, so your numerator would be 18 out of 25. So an OR, you've got like sections or parts to put together. The probability of something occurring and the probability of it not occurring differs by like 100%, or if in fraction form, the whole number 1. For instance, if they say, like over the weekend, it was an 80% chance of rain, what's the chance that it was not going to rain? 20%. So those two probabilities add together to 100%. If we gave the probability in fractions, we'd say the probability of it raining is 4/5, the probability of it not raining is 1/5. The 4/5 and the 1/5 add together to be a whole unit. So this is reminding you, you can subtract to find the probability of something not happening. Some of the questions that you'll be asked is, what's the probability of it not happening, like this one. I want the probability that the point is not on segment QR. That could be done two ways. You could find the probability of it being on QR and subtract, or you can look at where is it not going to be on QR and add that up like the OR idea. So where is it not on segment QR? Right here it's not, right here it's not. So you could do like we did those last problems, 12 out of 25. If you wanted to use the idea that I was just referring to with the not, the probability of it being on QR would be 13 out of 25. So the probability of it not being on QR would be 1 minus 13/25, which you'd have to think of as 25/25 minus 13/25, which is 12/25. I guess whichever way. First way was a lot simpler, but you can do the subtraction to find when it's not there. How about probability that a point is on BD? I want you to grab your marker board so that I can see that your brain is registering correctly. The point is on segment BD. Let's go fraction and reduce if possible. More to see. All right, that one reduces to be 2/3. Correct. Okay, now you have to make a model for this one. This one is like a little story, but we're going to put it into a number line. We have an antivirus program that has the following cycle. So the whole number line is going to show scanning for 15 minutes, displaying results for 5 minutes, sleeping for 40 minutes. So make a number line that shows those sections. 15 minutes of scanning, 5 minutes of displaying, and 40 minutes of sleeping. Mark the section so you know what's what. So how long is the whole cycle? The whole cycle is 60 minutes? Okay. So with that in mind, find the probability that the program will be scanning when you arrive at the computer. So why did I ask what the whole cycle is? That's your denominator. The whole cycle is your denominator. Yes. Yeah, I wouldn't get rid of that one. There's probably another question about it. That should come up with a 15 out of 60, which reduces 1/4, or 25%. Looks like I didn't do another one on that. Okay, so a new number line, and you might want this one in your notes. Pedestrian signal at a crosswalk has the following cycle. Walk for 45 seconds, don't walk for 70 seconds. The reason you might want it in your notes is some of the questions asked about it. Not that it's a difficult cycle. Walk for 45 seconds, don't walk for 70 seconds. So how long is the whole cycle? 115 seconds. Okay, so when we do our probabilities, it's going to be out of 115. Okay, so what am I interested in? What's the probability the signal will show walk when you arrive? How many out of 115? The walk part was 45. You're on 45 out of 115. Reduces to be? I'm seeing 9/25. Okay. Was it 9/25 or 9/23? Okay. As I said that, it didn't seem right. Okay, so now on that same one, what's the probability that you, when you get to this sign, you'll have to stop and wait more than 40 seconds? Now, there's not a section that's labeled wait. So what part of this number line would you be waiting? Basically in the don't walk part, right? But I'm not interested in the whole 70 seconds of don't walk. I'm interested in just waiting more than 40 seconds. So we kind of need to divide that don't walk part. So in that don't walk part, there's 70 seconds total. Let's split, let's go 40 seconds here, then how many seconds is left here? 30. So what part now is where we have to stop and wait more than 40 seconds? Is that the 40-second part or the 30-second part? Yeah, the 30-second, this would be where you're waiting more than 40 seconds. Because if you were in the 40-second part, you would be waiting or not walking 40 seconds or less. The question is asking waiting more than 40 seconds. So since that's our section, our probability is going to be 30 out of 115. Scribble here. Is that making sense? Why it's that section? Why it's 30 seconds? Give me a thumbs up or down if that made sense. Okay. All right. What if you arrive at the signal 50 times? Predict how many times you'll have to wait to stop, or have to stop and wait more than 40 seconds. Now this answer is not a probability. This is how many times. And if we're going there 50 times, it's going to be less than 50. So what was our probability of waiting more than 40 seconds? We just had that, didn't we? 6 out of 23 when you reduce it? Okay, so we want to know how many times out of 50 we would have to do that. Understand how I can do the probability, or the probability with the proportion? So when you cross multiply 300 divided by 23, which is 13.04. So how would we answer this question? How many times? 13. I think we'd say about 13 times. About 13 times. So about 13 times out of 50, when we come to this signal, we have to stop and wait more than 40 seconds. So what did I use? I used the probability of what I'm interested in and saying how many times out of 50 that would happen. Clarifying questions? Okay. What's the probability that the light will not be red? Not red. This is not out of 60. 27 out of 57. I don't think that reduces very nicely. So they went to decimal, but a fraction I think is fine. If you arrive at the sign 20 times in a day, how many times would you expect the light to be green? This is one like I set up just a little bit ago. Cross multiply. So how many times out of 20 would it be green? You'll have to figure out what your probability of green is. How many times out of 20? So this is the probability of green, but I don't know how many times out of 20. Set that equal to 7 out of 20. A few more. And just to check, you would be going, how many out of 20 is 22 out of 57? That's what you're cross multiplying. And it comes out about 8 times. Correct. Okay, I'm going to skip this one in order to get to the other type and still do our quiz. Right, use the spinner to find the probability. Now this is the type where we're just going to compare the angles. The pointer lands on yellow. What's the probability? Well, how many degrees in the section that is yellow? 140 out of, should be 360 when you add those all up. So simply 140 out of 360 reduces to 7/18. Probability that the pointer lands on blue or red. 112 out of 360. With the or, you're adding those sections together, just like we did on the number line. Pointer not landing on green. I know I'm going real quick because I guess I'm not thinking I need to spend all that much time on these. Okay, the on green, no, or not landing on green. You can do this the not 2 ways. You can either get the probability of it happening and subtract, or add up all the regions where it's not green, like an or would be. Personally, I do more where I add up the regions where it's not green. So how much did all of these add together? 252 out of 360. 7/10. The spinners, I think, will be something that you'll easily, naturally do. Okay, and I'm going to skip that one. Okay, then the last type was areas. Area. This is why I thought it'd be good to do the lesson before you finish up your quiz. Because when we do the area probability, you have to find the area of the regions and set up your ratios to compare. Okay, so we're looking for the point chosen randomly inside the whole rectangle is each shape. So let's see. What's the probability that a point would be in the circle? What we need to figure is what's the area of the circle compared to the area of the whole thing, which is a rectangle. So area of the circle. 18 is the diameter. So the radius is 9. So the area of the circle would be pi times 9 squared. Pi r squared is the area of the circle. 81 pi. Out of the area of the whole rectangle. The rectangle is 50 by 28. 50 times 28 is how much? One, 400. So we have 81 pi out of 1400. It does say round to the nearest tenth because this fraction doesn't reduce very well with the pi one part, not the other. So 81 times pi divided by 1,400 to the nearest hundredth, I would get 0.18. Questions over there? Anything? Nothing? Okay. All right. What's the probability that the point is in the trapezoid? In other words, if I were trying to hit the target, what's the probability I'd hit the trapezoid? Find the area of the trapezoid, everybody. Time for you to work, not me. Find the area of the trapezoid. Trapezoid is 1/2 base 1 plus base 2 times the height. That's your numerator. Your denominator is still the whole rectangle. I remember what that number was. What's the numerator? Area of the trapezoid? 322? Yeah. Agree with that? Yes. They're kind of indicating no. 34 plus 60, or 34 plus 16 is 50. Half of 15 is 20, 50 is 25 times 18, about 450. 450 divided by 1400, about 0.32. About 32% is the trapezoid. And then how about the squares? There's more than one square. So what's the probability that a point would be in either one of the squares? This is like an OR. What's the area of one square? 10 times 10. 100. Two of them. So 200 out of 1,400. We were going to decimal 0.14. Decimal. So what you're doing when you do the area probabilities, you're finding the area of the shape you're interested in compared to the whole thing. Now they're going to make some pictures a little bit more difficult. So this one maybe is a little bit more tricky. And look what we're looking for. Find the probability that a point chosen randomly inside the rectangle is not inside the equilateral, triangle, circle, or trapezoid, round to the nearest hundredth. So if we're interested in the probability of it not being in these little shapes, we're talking about all this light blue part. If it hits any place in there, that's what we want. So what would you do with your numerator? I know the denominator is gonna be just 45 times 20, the area of the whole thing. How would you do the probability of it not being in these shapes? Okay, do which way? Add up there the little shapes, okay, and then did you say subtract from the total? Okay, like we're taking them out. Now be careful, if you take out the circle and the triangle, you're taking out the circle twice. So really you don't even have to worry about the circle. If you would find the area of the triangle and subtract that, you're automatically subtracting the circle. And then the area of the trapezoid. If you're looking at measurements on the triangle, you have basically like the apothem. You might have to do your, let's review before you take your quiz here. Central angle, how many degrees? Okay, 360 for all of them. My central angle would be 360 divided by 3, so it's 120. Put in the apothem, now the angle is 60. And if I'm interested in finding the perimeter, I would need this part. It is a 30, 60, 90, so I could quickly get that it's 6 times the square root of 3. A lot of times they're not, so we used a trig ratio. Opposite and adjacent would be tangent. You could use the tangent in order to find it. That just kind of gives you a review on how you got to that. Overall, how do you find the area of a regular polygon? 1/2 apothem times perimeter. Remember that? All right, yep, we'll stop there as far as our lesson. Let's write down which problems to do. And what do you have us do tomorrow? That project about your mathematician. Hopefully you did not put it off till tonight. Okay, mathematician project. If you need any poster paper, it's on top of the file cabinets by the door. You can print it off and then present it so that it can be put up on the wall. Look through the rubric to make sure that you have done everything